Okay, this is our first lesson on equilibrium, and this is just going to take us into an intro into what equilibrium is and what are some of the implications and some of the factors that affect equilibrium. So, you may ask yourself, what is equilibrium? Well, equilibrium is a state in which something appears to be the same, although opposing processes are occurring at the same time. I like to think of equilibrium as a balance myself. You have like a teeter-totter where you have forces pressing down on either side, but everything is balanced at that point. Depending on where you put the fulcrum, you can have different size masses actually balance out. Well, equilibrium is sort of the same thing when it comes to chemical reactions or changing of state, or even substances dissolving into one another. So what we're taking a look at here is an example of, we've got a bottle of pop, poorly drawn, but it's a bottle of pop. And you decide you want to drink that bottle of pop, so you take the lid off. And of course you notice the fizzing occurring. And what is that fizzing caused by? Well, it's caused by the creation of carbon dioxide bubbles. And that's from carbonic acid inside the pop. We bubble carbon dioxide into a beverage, it produces carbonic acid, and that acid will break down. Now, what caused this change? Well, what we probably notice is that there's some pressure when the lid is on, and you can probably feel it. When you take the lid off, you release the pressure, and at that point carbon dioxide starts to bubble out of the solution. Now, if you give your pop a long time to just sit there and not consume it, which I'm sure is hard to do, after a while you'll notice that there's no more bubbles forming and leaving, and you might think at that point that all the carbon dioxide is gone from the pop. You might shake it a little bit, sometimes add a little bit of sugar, and you notice that, oh, some more bubbles are going. So what does that tell you? It tells you that at this point the carbon dioxide doesn't look like it's leaving, but it's still present. So if we were to take a snapshot at the microscopic level, we would notice some things happening. We would notice that we have CO2 gas and we have CO2 in solution. And what's happening at this point, when we can't see any bubbles leaving, is there are still carbon dioxide molecules that are evolving out of the solution. They are, but they're so few that we can't see it with our eye. But what we've reached is an equilibrium point where the number of CO2 molecules are going back into solution. Now, this is very, very slow. Indeed, it's so slow that when you take your breath right now, the carbon dioxide that you are breathing out would take, half of it would take about 100 years for it to be dissolved back into water, say in the oceans or lakes. So that process is very slow. So in the change of state from aqueous to gas, the equilibrium is much more favored towards going from dissolved carbon dioxide into gaseous carbon dioxide. Now we're just going to quickly take a look at the different types of equilibrium out there. We have solubility equilibrium, we have phase equilibrium, and we have chemical reaction equilibrium. We're just going to quickly take a look at what each of these are. In the case of solubility equilibrium, that involves a substance's ability to dissolve, sort of like our last activity where we saw carbon dioxide dissolved into water and then leaving. Say you take some copper to sulfate and you crystals, you put them into water, you'll notice that you get a blue color in the water, and that blue color is coming from the copper ions. However, what you'll probably notice over time is that perhaps not all the salt dissolves. So what's happening there? Well, what's happening is initially the blue color will get more and more or the water will get more and more blue until it reaches a point where the salt can no longer dissolve. Most salts, all salts hit a point where the solution becomes so saturated, or their solubility is such that you can't dissolve anything else, any more salt into the solution. At that point, the number of ions forming from the salt and the number of ions recombining to form the salt again are equal, and at that point we have our equilibrium. Now, of course, that for most salts that doesn't happen right away. Now, phase equilibrium is when we're changing the state of a substance, and a good example is water going from a liquid to a vapor. At 100 degrees Celsius at standard pressure, water will go from a liquid to a vapor. However, this process is actually favored if the pressure decreases. English explorers going up, climbing up mountains, the really high ones, would comment that their tea never tasted so good because they were up, when they got up really high, the water would boil at a much lower temperature. So altering pressure can affect this, and we know that as well, especially if you've ever boiled water on a stove. If you go from a closed system, say your pot on the stove has got the lid on it, and then you take the lid off, you'll notice that your water will start to boil much faster. And in many cases, opening your system will cause an increase or a shift, in the equilibrium towards making more vapor. Now, the last one is chemical reaction equilibrium. We're going to take a look at this throughout this unit. That involves reactants producing a product, but you have to look at it as reactants are actually on both sides of the equation, and look at reactions as either being forward or reverse. So in the case of calcium carbonate reacting to form calcium oxide and carbon dioxide, the forward reaction would be what I just explained there. However, calcium oxide and carbon dioxide can react again to form calcium carbonate. And there are many factors that will affect how that happens. Some reactions will proceed to completion, say 100% of the products. Good examples are usually oxidation reactions where you're burning, combusting a fuel. But some reactions will only make it, say, to around 50%, and some reactions will go to even less than that. So, at this point, we're going to go on to video number 2, where we take a look at some models that show different types of reactions and model what actually happens at the molecular level for different types of equilibrium reactions.